question because we basically will use the Lorentz series to classify singularity. Okay. So first, we are talking about isolated singularity. The isolated singularity means the function. So you have the function is analytic over a large region, except maybe isolated point that is not analytic, or you can say that they either go to infinity or somehow the Cauchy-Riemann condition is not satisfied, or is becomes multi-valued. Later on we'll talk about branch point. But the idea is what we call isolated is it's not and only on a point. So you go just a little bit infinitesimally around it. It's still analytic. Okay, so they happen only isolated point. Okay, so that is important because if it's not that, then some of these things we talk about will not work. Okay, and the example for non-isolated one. So we check that like the complex conjugate function is not analytic, right? Have we checked that it's not analytic over a large region, so it's not isolated. The singularity doesn't have to be infinity, but most of the singularity that we talk about would be actually goes to infinity. Okay, and so the textbook talk about two kinds of singularity. You have the poles, or you can extend that to poles of different order, and poles of infinite order, and the textbook called essential singularity. Right. There's one more classification of singularities, isolated singularity. The textbook didn't talk about, but you use that actually. The book use that in some of these example later when you do integration. It's called removable singularity. Okay. Okay. Removable singularities. This happen isolated point that the function is not well defined, but we can redefine it so that to make it totally analytic again. So one of the situations that the text will talk about is, say you have a function, you want to do an integration somehow, like sine g of c. Right. So obviously, at 0 is not defined because you have 0 divided by 0, and it's not defined. So you can define f0 as the limit. 0 as define it as limit. Say v goes to 0. That is 0 to 0. Right? You redefine that, and it becomes anything again. Or if you define it like using your Taylor expansion or the infinite series expansion, and you see that that's not singular because sine c, the expansion is c minus dq over 3 factorial and so on. And you divide it by c. If you use the Taylor expansion, then obviously you cancel the c, and it's not singular again. But this is exactly like it actually is. A series expansion is like taking a limit. So what we call is you can remove the singularity. Okay, that and sometimes the useful thing about this is that it's not really singular. Really singular is just a regular point if you remove the singularity. So like you integrate this f along the z-axis. So, along with z, you have integration along with z of this function or something similar. So you have a removable singularity here. And because it's removable, then you can actually remove it from the integration. Just choose a distance delta away from it from both sides. The integration will skip this point. Okay, just skip it. As long as delta goes to zero, because it's a regular point. You skip one point, doesn't change the integral. Okay, okay. I'm talking about the integral, like x dx. You integrate that, right? And that it doesn't you can skip that, and this is called the principal value. And later on, we'll talk about it again. And the reason you skip that is sometimes you want to, after you skip that, you want to separate the function into two parts. Now you now it doesn't have this cancellations like sine z. Is 1 over 2i into the I z minus e to the minus, right? If we divide it by z, then this one is removable, but each term is not removable. This one divided by z is true singularity. This one divided by pi is also true singularity. So basically, you can remove uh, that singularity in original function, but sometimes you want to separate into two parts or more parts that is not that become truly singular. But because it's originally removable, we can remove this point from the integration source. Then you don't need to worry about this singularity. So each term, the singularity, you can actually remove by this principal value already. Okay, so and the reason we like to use exponential function to do integration like that is will become apparent later on. We'll have some mathematical theorem to show that the exponential function is easier to do integration. So we want to separate into that kind of term. Okay, so that's just one addition to your textbook. We call removable singularity. Then another singularity are the poles. Right? So, yeah, so, the language of the text at v sub 0 is singular, and especially for poles actually goes to infinity. Okay, so c tends to c0 equals infinity. Right? Then we can do a Lorentz, say if this is c0, c sub 0. We can take out a little bit around it, and before going to the next singularity, you have an annular region, and within the annular region, we can define a Lorentz. We can find a Lorentz series expansion for this f within this annular region. So that we did before, right? So within this region, we say that it's m. Yeah. Lorentz series, because it's a singularity, then we could go to negative power. And now the separation classification is that some poles will have a sub n truncated in the negative uh, negative value of n. So if an equals 0 for that's how to put it, because we're already using n. It doesn't matter that much. Okay. for let's define another integer for n less than m, which is less than 0, right? So you can do -1, -2, right? If it's all 0, so all this coefficient is 0 after a certain negative power term, then this singularity is of the order m. So like if you the the one that's non-zero is a -1, right? And then a -2 is 0, and so on. A -3 is 0, and all that. Then this is the pole of the first order, or we usually call it a simple pole. Okay, so that's the usual case. Many cases, not always. Okay, so that defines the order. So if it is -2 is not 0, but -3 is 0, and so on, then it's the second order, and so on. Okay, so it depends on the coefficient of the Lorentz series. When do you have the last non-zero coefficient, and that will define your order. Okay, and the order is important because later on the poles of different order the to calculate the residue, so-called residue, we'll use different formulas, slightly different formulas. Okay, so and then there are series that an are non-zero for all n, or for all negative n, I should say. It can truncate in positive n, doesn't matter. Then. It's still essential singularity. So for n tends to minus. Okay, then that's called essential singularity. And so that separation is that to calculate the residue of the for essential singularity, we need the Lorentz series. We need to find the Lorentz series and find the a-1 coefficient, which is what we later call residue. Okay. So essential singularity is you don't have formula, well, and you just need to somehow found the coefficient. Well, you have a formula of the integration, but usually that integration may not be that easy to integrate out. So somehow you can find a expansion of the Lorentz series around the singularity, the essential singularity, then you can get it. So one the example for essential singularity is like e to the 1 over c. Yeah, obviously that is 1 plus 1 over c plus c squared, c factorial, and so on, right? That's like you're doing the Taylor expansion of a function like 1 over c as your variable. You do a Taylor expansion, then you get an expansion, get a series with inverse power of c. And this is a Lorentz series. And a-1 coefficient is here 1 at c equals 0. Okay, but it has all power, so this is an infinite order pole, and all the formula for calculating residue using the pole formula will not work. So you need to be a little careful. If you encounter essential singularity in your integration, you need to find the series, find the Lorentz series. Okay. So that is that. Yeah.
Suppose the
Yeah.
with the a-1 or the a-1 term, that's the 1 over c, or no? What's the
This will be here.
yeah
1 over c times coefficient in this case is 1.
okay, and then if you plug, is that how you also get the residue then?
This will be the residue at 0.
Okay.
This is the a-1.
Yeah.
Okay. when after you get the Lorentz series, look for the 1 over z coefficient of 1 over z or z minus sub c sub 0. Okay, and that is how we do it.